So in your do now activity, it says, what is the difference between a covalent bond and an intermolecular force? And you were correct in your answers. Covalent bonds are bonds within the molecule. Covalent bonds are formed through a sharing of electrons, either 1, 2, or 3 pairs. For example, carbon dioxide has 2 double bonds, and those are covalent. Intermolecular forces are the forces between molecules, so between the 2 carbon dioxide molecules. Why is carbon dioxide a nonpolar covalent compound, even though it has covalent bonds?
The oxygens are pulling at, or being pulled away from each other, but at the same exact amount of energy.
Pretty much. So what you've got here is you have a dipole here and a dipole here, and they are pulling with equal force, so they cancel. Is this molecule symmetrical?
Yeah.
Yes, it is. So as a result, the dipoles cancel and you have a nonpolar covalent molecule. So if you have nonpolar covalent molecules, what is the only intermolecular force that can form between the 2 carbon dioxide molecules? LDFs. And for those of you, you're like, oh, what is LDF? We're going to go over all of it. It's a few things you probably learned in honors. If not, don't worry. Please remember that covalent bonds are much, much stronger than intermolecular forces. A covalent bond is an intramolecular force. Intra means within, as opposed to an intermolecular force. Intermolecular forces include LDFs, dipole to dipole, and hydrogen bonds, as you said. And in this particular example, because you have a nonpolar covalent molecule, the only type of IMF that can form are London dispersion forces. And we're going to go back and either review these intermolecular forces or teach them from scratch. So that's what we're going to get into in this particular chapter. And I'll go over what's coming down the pike this week and next so you know exactly what to expect and when. Same learning goal we've been talking about almost the entire quarter. This is big idea 2. Critically important. You'll see a lot of multiple choice questions and possibly some part 2 questions for big idea 2. Students will be able to demonstrate that chemical and physical properties of materials can be explained by the structure and the arrangement of atoms, ions, or molecules, and the forces between them. And you'll see that the forces between them, these intermolecular forces, will determine properties such as boiling point, melting point, vapor pressure, etc. And that's what we're going to be looking at here. So we're going to review a little bit in regard to states of matter, and the do now really helped summarize inter versus intramolecular forces. And what we're going to see here, we know bonds are intra, within, and that's going to determine shape and dipole moment, polarity, etc. Intermolecular forces, and this is what you had said, Maddie, these are the forces that exist between molecules, and they're going to determine the physical properties of liquids and solids. And you'll see, for example, if you look at the periodic table shown right here in group 17, your halogens, fluorine and chlorine, F2Cl2, are both gases. Bromine, Br2, is a liquid. I2, iodine, is a solid. So you can have all 3 states of matter, and that is based on the intermolecular forces that form between these types of molecules. And we'll take a closer look at that as we go. In terms of states of matter, you are, of course, aware, since you have been little, that we can have solids, liquids, or gases. And you're going to see water in the solid, liquid, and then gaseous phase here. And water in the solid state, here's oxygen, here are the 2 hydrogens, the bent design with a bond angle of 104.5. And again, a lot of what you learned in the previous 2 chapters are going to come back here. You have to be able to draw compounds. You have to be able to determine polar or nonpolar. So what you see here is the molecules are just vibrating in a fixed position. They're not moving around freely. There's intermolecular forces between the water molecules. What intermolecular forces exist between water molecules?
Hydrogen bonds
Hydrogen bonds,
and dipole
dipole to dipole, and LDF. If something has hydrogen bonds, it has all three because it's polar covalent with hydrogen bonding capability. Therefore, it has dipole to dipole interactions and LDS. And if this sounds foreign to you, don't panic. I'm going to go over all the different types of IMFs in great detail. So solid. Water in the liquid state, what can you see here compared to the solid state? They're moving more freely. So would you say they have greater or weaker IMFs? Weaker. They still have all three, but you don't have as many forming. So now you're getting more movement, less particle arrangement, and then finally in the gaseous state, what you're seeing now is the particles are moving around very rapidly, and you know from our chapter on gases that there really are no intermolecular forces forming between the molecules as they move around very, very rapidly. All right? And everything we just looked at is in your notes here as well. Now you'll see that liquid and solid states do show some similarities. If we look, for example, at the density of water as a solid, liquid, and gas, you'll see that the solid and liquid have pretty similar densities, but the density of gas is considerably less. Why would gaseous water or water vapor have a lower density than water in the solid or liquid state? And then I'll take your question.
Because there's less molecules per volume.
Let's say we have the same mass for each one.
It takes up a bigger volume.
Exactly. So with a gas, you've got the entire volume, not just what fills up the container. You have the whole container. You got it. So the greater the volume, the lower the density.
You said the intermolecular forces determine the physical properties of liquids and solids, but not gases.
Do gases have intermolecular forces? And there's your answer right there. You got it. So you can see here that gases are going to have a lower density. They have a larger volume. And this is interesting as well because water is one of the few liquids that actually expands when it freezes. So it's going to have a greater volume, hence a smaller density as compared to the liquid. And we'll get into that a little bit later. And in this particular chapter, we're going to focus on liquids and solids and the forces that cause them to generate this state of matter. So with intermolecular forces, which are abbreviated IMFs, we're going to talk about them for covalent molecules. With ionic compounds, you have interionic interactions, and we'll get to that later on. You'll see ionic compounds will boil and melt at much higher temperatures than covalent ones. An interionic interaction is much stronger than any of the IMFs that we're going to talk about here. So as you guys said earlier, these exist between molecules, and you've mentioned some IMFs already, and we're going to talk about each one, give examples, and make sure that we know explanations. Initially, I'm just going to have you fill in words so that you've got it, but you've got to be able to explain this on your own. This is a very explanation-based chapter. We'll get more into the mathy stuff in the third 9 weeks, which some of you, I think, will much prefer. But this is not difficult. The first type of IMF is the weakest. It's London dispersion forces, abbreviated LDF, named London dispersion forces for Fritz London, who discovered them. Sometimes people will just say dispersion forces. These are forces of attraction between an instantaneous and induced dipole in nonpolar covalent molecules. Nonpolar covalent molecules don't have dipole moments. They will have a net zero dipole moment. Perhaps the bonds are polar, but the bond polarity can cancel as a result of perfect symmetry, and so the molecule as a whole will be nonpolar covalent. When you talk about an instantaneous dipole, let's take a look at an instantaneous dipole with the following schematic. We're going to have two nonpolar or unpolarized molecules. when they get near one another, an instantaneous dipole forms. The electrons now shift in such a way that you get an instantaneous dipole, such that there's more negative partial charge here than here. More negative partial charge here than here. So you get what's known as an instantaneous dipole. Sometimes an instantaneous dipole can then induce an instantaneous dipole in another molecule, and we'll take a look at that. As the molecules move apart from one another, the dipole is gone, and so it doesn't last very long.
In solid carbon dioxide,
I don't know why that
in
happens here.
solid carbon dioxide, dry ice, nonpolar molecules are arranged close to one another in a regular array where they move slightly around an average position. The distribution of electrons in a molecule can occasionally become asymmetrical, leading to the formation of a temporary separation
So here's the instantaneous dipole in this molecule, and look what happens.
of charges, a dipole. Partial changes on the molecule that form a temporary dipole then influence the electron clouds of nearby molecules. Although the dipoles are temporary, there is a significant attractive force between adjacent molecules as a result of the deformation of their electron clouds. These attractive forces are called London dispersion forces. London dispersion forces are the only type of intermolecular force found in nonpolar molecules.
So nonpolar covalent molecules only have one type of intermolecular force, and that's a London dispersion force. It's going to be the weakest of those IMFs. And that's why nonpolar covalent substances will boil and melt at lower temperatures than polar covalent substances in most cases.
With the dipole that's formed, why does that happen? Just because the other one is coming closer?
It basically causes a shift in the electrons in the covalent bond temporarily. So it's like just pushing something almost not completely out of the way, but just pushing it slightly.
Why does the shift occur?
Because as another molecule comes near it, it will upset the distribution of electrons, probably because there may be, even though it's a nonpolar covalent molecule, if you think about something like carbon dioxide, there was a dipole, the dipole is canceled, so if something moves near it, that may cause a shift in the electrons in the bond, causing a redistribution temporarily. Sort of like if you're driving somewhere and there's an accident, they might put a detour up, you're going to go around. If you're shopping in Home Depot and they're cleaning that aisle, they'll put their little chain and you have to go around or you can't go down that aisle. I think it's pretty similar to something like that. 60-foot fence? What do you need that for?
Last
To
period,
keep a goat.
Mr. Mars
last
goat.
period, Mr. Mars said he went shopping for 60 feet of fencing for his pet goat.
This man's
He
really.
needs goat cheese to his goat.
He doesn't actually have a goat.
No.
Wonderful. In any event, with London dispersion forces, you saw the instantaneous dipole, you saw an induced dipole as well. Here's the key now. This is something you wouldn't have focused on in honors, but something you are going to need to understand in AP. And this is the concept known as polarizability, and this is the measure of ease with which the electron charge density is distorted. So certain molecules can have more distortion than others, and that's what you're going to be looking at here, and we'll talk about what causes a molecule to be more polarizable than another molecule. It says large atoms are more polarizable than small ones because they have more electrons, and those electrons are going to be located farther from the nucleus, and this may help address your question. As those electrons are farther from the nucleus, it's probably going to be easier for greater distortion because their positive charge of the nucleus will have less of an effect, as those electrons are farther from the nucleus with more electron shielding. The greater the polarizability of molecules, the stronger the IMFs between them, leading to higher melting and boiling points. And that's what you're going to see with the halogens as well as with the noble gases. So if you looked at the periodic table here, fluorine is a gas, F2. Bromine is a liquid, Br2. Well, fluorine has 18 electrons, and bromine, Br2, has 70. So the more electrons it has, the more polarizable, the greater it is to distort those electron clouds, and as a result, this has more LDFs than this. This substance is a liquid at room temperature, whereas fluorine is a gas. If you consider strength of LDFs as you go down group 18, which one's going to be more polarizable, xenon or neon? Xenon. Xenon has 54 electrons as compared to neon's 10. The greater the number of electrons, the more polarizable, the stronger its LDFs. You also see greater LDF strength in an elongated molecule compared to a compact one. And as you have an elongated molecule, you have greater surface area, you have more sites with which you can form dispersion forces, hence the greater melting or boiling point.
What about an ion?
An ion would not be a covalent compound.
Oh.
And that was a big whoop to do on the test. Yeah. All right.
Dr. Kim, how would you know if a molecule's elongated or not?
So for example, oh, you're going to love this example.
Am I?
Yeah, you will. This has your name all over it. Let's say you have something like this. I'm going to draw it crude. CH3, CH2. I'm not putting the H's all over. One, two, three, four, five. This is pentane as opposed to this one's elongated as compared to this more compact one. So you would guess that this has the higher boiling point and melting point. What's the only type of IMF that both of these molecules can have? LDF, because they're both right. But this one's more elongated.
How did you? Okay, the first one has like 2 CH3s and 3 CH2s, but the other one.
Count the H's.
Okay.
You're asking why it has that?
Are they just isomers that have different bonds?
Yeah, they're isomers.
Okay.
They have the same molecular formula, different structural formula. Glucose and fructose are isomers too,
Really?
Yeah.
Then why do they do different things too?
because of their structure.
Wait, why would, so the other one would have a greater boiling point and melting point because they have greater polarity?
Now, you got to be careful there. The polarizability here is essentially the same because they have the same number of electrons, but this molecule is more elongated than this, so this has more sites with which the LDFs can form than this one.
Why isn't the melting point lower? Like,
Because you
Boiling
have
point
more
and melting
sites
point
with
is-
which LDFs can form. So it takes a higher temperature for the substance to melt or boil because you have to break more LDFs.
Melting and boiling are both like, if you're going up the ladder, they're both going up
but
and
is
then
it?
freezing and.
Wouldn't there like structurally? Wouldn't there be a larger surface area?
Yes, so there are more sites to form LDFs, so more LDFs have to break, so it takes a higher temperature to boil or melt.
Okay.
Another type of intermolecular force is a dipole to dipole force, and you're going to see permanent dipoles aligning in a particular manner. For example, if you had hydrogen chloride, chlorine's more electronegative than hydrogen, so the dipole in this direction, and you'll see that the hydrogen chloride molecules will align themselves in such a way that you'll have partial positive, partial negative, partial negative, etc. So the dipoles align themselves in a particular fashion. So this is a polar covalent molecule, and now the IMFs that form for polar covalent molecules include LDFs and dipole to dipole forces or interactions, dip to dip to abbreviate.
Why isn't it hydrogen bonds? It shows hydrogen.
A hydrogen bond is a special type of dipole to dipole, and the hydrogen must be covalently linked to an O, N, or F, and we'll take a look at that one in just a minute. You'll remember. So if we were to look at the dipole to dipole, now this one actually could have hydrogen bonding. They used a different example than I did, but I purposely didn't use this
Bonds
one.
between atoms with different electronegativities have a permanent dipole, that is, a separation of charges, because of the unequal sharing of electrons. Some molecules which contain polar bonds do not have a net dipole. For example, carbon tetrachloride has polar carbon-chloride bonds, but the polarities cancel as a result of its symmetrical structure. It is therefore a nonpolar molecule. Even though the chloroform molecule has a tetrahedral shape, one of the outer atoms is different from the others, so the molecule is not symmetrical. This means the bond dipoles do not cancel, and the molecule has an overall dipole moment. It is polar. Molecules such as sulfur dioxide have asymmetrical structures due to one or more unshared pairs of electrons on the central atom. Sulfur dioxide is an asymmetrical molecule with polar bonds, therefore it is a polar molecule. When polar molecules, such as sulfur dioxide, are close to one another, they tend to align so that the positive end of one molecule points towards the negative end of another molecule. Attractions among polar molecules are called dipole-dipole forces.
Couple things you want to make note of here. A permanent dipole can of course induce a dipole in another molecule. Polar covalent molecules have both dipole to dipole forces and LDFs, and that's why typically you're going to find that polar covalent molecules will boil and melt at higher temperatures than nonpolar. Not always, but typically. If you're going to guess, you're going to guess that polar covalent molecules have higher melting and boiling points than nonpolar ones, unless they tell you differently. And I'll give you an example there, probably as you do now tomorrow. Dipole to dipole forces are much, much weaker than covalent bonds. They're only about 1% as strong. And what you find is those molecules get farther and farther apart from one another, the dipole to dipole interaction strength will decrease. It says these forces are relatively unimportant in the gas phase at low pressure. How come? What do you know about gases? They move really, really quickly, and they don't have intermolecular forces between those gaseous particles, okay? Looking at the table here, and let's keep this very simple, we've got the molar mass, the substance is polar and nonpolar, whether it has a dipole moment, and its boiling point in Kelvin. Looking at the chart, which substance has the greatest boiling point? Carbon monoxide. Why? So a lot of you are saying it's polar, and that is why it has a higher boiling point, but that's not your explanation, so you have to be careful there. Carbon monoxide is a polar covalent molecule. It has IMFs that include dipole to dipole forces and LDFs, whereas the nonpolar covalent molecules only have IMFs that are LDFs. weaker than the combination of the LDF dipole to dipole. Also note, because sometimes they don't tell you polar or nonpolar, but they'll give you a dipole moment, which molecule has a non-zero dipole moment? Carbon monoxide, and that's because it's polar. All right? Be careful there. In general, the greater the IMFs, the higher melting and boiling point. And we already talked about some of this here. With more electrons and elongation, London dispersion force increases in strength. We said typically polar molecules will have stronger IMFs because they have both types as opposed to nonpolar. So they're going to have higher boiling and melting points. This line I added in earlier today. There are some exceptions. I'm going to open up, I think, with your do now tomorrow on that. It'll be a good one to hit. LDFs are in all covalent molecules, not just nonpolar covalent. So it says consider two nonpolar substances, bromine chloride and iodine bromide. One is a solid at room temp, the other is a gas. Identify the solid and the gas. So which one would be a solid and which one would be a gas, and why?
Iodine bromide would be the solid, because iodine is solid and room temperature and bromine liquid.
You're correct in your selection.
I think it's because it has more electrons and is therefore more polarized.
Yeah.
I'm gonna say that.
But I applaud you for going out on a limb there.
I was ready.
We're on film. You're going to walk in the film right there.
Say hi, just say hi.
Can you hit me with about 5 minutes left?
Yeah. The admin set me up, so I'll come back.
5 minutes left.
5 minutes will do.
So what time does the bell ring?
7:06.
I'll see you at
10 minutes?
It rings at 11:08. I'll see you at 11:03.
Okay.
All right.
All right, thanks.
Don't be late. Please.
So what we have here is both compounds have bromine in them. Both compounds have bromine, so you're comparing chlorine and iodine, and you are correct. Iodine has more electrons. It's therefore more polarizable. It's going to have greater LDF strength. Hence, you're getting that transition to a different state of matter. All right? The other type of IMF we want to mention are hydrogen bonds. And a hydrogen bond is a special type of dipole to dipole interaction. Actually, that's changed because when I grew up, like 10 years ago, hydrogen bonds were just different. Now they're saying it's a special type of dipole to dipole. And what you find here is the hydrogen is going to be covalently bonded to an NO or F. So for example, here's a water molecule. This H is covalently linked to the O, but what happens is it can hydrogen bond, form a relatively strong type of intermolecular force, stronger than your typical dipole to dipole interaction. And you can form a hydrogen bond between an H that's covalently bonded to an O, N, or F, or an O, N, or F on another molecule. So water has the ability to hydrogen bond. So does ammonia, for example. So does hydrogen fluoride. Now this is a little bit dangerous drawing this all together because some of these molecules might be able to interact. But these are hydrogen bonds. You have to be able to draw them in. You have to be able to recognize them. I've seen a lot of very easy multiple choice and part 2 questions, and you can't miss these. They're too easy. Did I make a boo-boo?
You said S, right?
Rarely S, rarely chlorine. So let's stay away from those. It's going to be N, O, or F. Fond.
So what happened? Is it possible for like H2, like a couple of H2Os, like two H2Os, and nitrogen dioxide, would it be possible to make, like, with the nitrogen dioxide, is it possible to make multiple hydrogen bonds at the same time? Does that make sense?
Mm-hmm.
There's no hydrogen in nitrogen dioxide.
Well, nitrogen dioxide.
Well, and water.
But there's NO2 and then
NO2 is dangerous because you've got a radical in there, and you could get a reaction going. But in regard to a hydrogen bond forming, I would say yes. Between the H on the water and either side, yeah, I'd say yes.
Can you have water on both sides at the same time?
Sure, why not? Yep. I just don't want to draw that because we've got a non-tester. All right, what you also find here is this helps explain why water boils at a higher temperature than what the trend on the periodic table would predict. Shown in your notes here, I'm going to blow this a little bit,
Oh, that's 25 eggs.
are the boiling points of covalent hydrides of the elements in groups 14, 15, 16, and 17. Your book still uses some of the old nomenclature. If we look at group 16 for a minute and we compare, and let's keep it simple, water with hydrogen sulfide. If you look at placement of elements on the periodic table, O, then S, selenium, and then tellurium, you'd expect an increase in the boiling point as you go down the periodic table because you're having more and more electrons, more polarizable, and as a result, you would expect that the boiling point increases. And this one's a little bit tricky because these are actually non-polar, but they're so much more polarizable that it doesn't follow what you would predict. In any event, though, you can see that water has a much higher boiling point than hydrogen sulfide. And why might that be the case? They're both polar covalent molecules. They both have LDFs and dipole to dipole, but water
That's hydrogen.
has the capability of forming hydrogen bonds, and as a result, its boiling point is higher. What could you say about hydrogen fluoride and hydrogen chloride? Both polar covalent molecules, LDF dip to dip, but hydrogen fluoride has the capability of hydrogen bonding, and as a result, its boiling point is higher. Does ammonia have the capability of forming hydrogen bonds? Sure does. And as a result, its boiling point will be higher as well. These are the three most common examples: carboxylic acids, COOs, and alcohols, OHs hooking to an R group. That also has hydrogen bonding
What
capability.
is the?
I'm sorry, somebody else was asking. I didn't catch it. Who has a question? No? Yes? No? Yes?
What is that antimony, what? The SbH3, what is that? Selenium, sorry.
Oh, SB.
SbH3, what is that?
Yeah.
Nothing I've ever used.
'Cause, yeah, that one,
They're just showing you the hydrides from group
SPH3.
15.
That's a 3.
Yeah, it's a 3.
yeah, so,
I think
Yeah,
they
because
got
they're
the-
giving antimony a 3+ there, and it's hooking with the hydride.
What's supposed to be like right under ammonia on that red?
It's showing where the
That's where you
trenches
would have
is.
predicted water would be if it couldn't
Oh.
hydrogen bond.
So they just didn't do the dotted line for the yellow and green, but it's the same thing.
Yeah, it would also go down there. Yep.
Okay.
Yep. And then it says, for each of the following substances, indicate whether hydrogen bonding through an available H is an important molecular force. So the substance has to have an H. So right away, you know this one is garbage. HI would be a? Good job.
Hydrogen
Oh,
bond.
yeah.
That does not have hydrogen bonding capability because the H is not covalently bonded to an N,
Oh,
an O, or an F. So HI would be no. HF would be yes. And then be careful before you guess.
It's yes 'cause it's a poly.
Be careful before you guess. This is where what you learned in the previous chapter is going to come back to either bless you or haunt you. Achoo to you too. So we've got this is an aldehyde, and this is an alcohol, not the type you drink. It is methanol. Which compound has an H capable of hydrogen bonding?
Methanol.
The second one.
The second one. So this is an alcohol. This is an aldehyde. Don't worry about it. You'll need it in AP Bio. But in any, and if you're going to take Chem 2 subject test, we'll clean this up at the end. You don't need it for AP. But alcohols have hydrogen bonding capability, and alcohols also are water soluble. This is how bartenders, for example, water down drinks. So this is your hydrogen bond. Make sure you can draw one. Make sure you can recognize one, and we'll take a look at a question so that you're confident that you can. This does not have an H capable of hydrogen bonding because the H is not covalently bonded to what? All right, whatever, you got it. In the other example here, it says indicate whether hydrogen bonding is an important intermolecular force. Absolutely for ammonia, never for methane. This is an alcohol, so this is a yes. Carboxyl group, this is a yes. Nah. Hydrogen peroxide's a yes. The H is covalently linked to the O. And you're going to find that hydrogen bonding is very important in regard to physical properties. Substances that have hydrogen bonding are going to have higher boiling and melting points than comparable ones, and that's why alcohols boil at much higher temperatures than ethers or ketones. For those of you who like to do any type of cooking with alcohols, you know you can get those big flames. Okay. A to T, C to G. What is this diagram of?
DNA.
DNA. And A pairs with T and C pairs through G through what? Hydrogen bonds. Which type of base pair melts at a lower temperature, an AT or a CG?
CG.
Which base pair melts at a lower temperature, AT or CG? AT, because you only have two hydrogen bonds compared to... No, I didn't.
The first time you did.
Okay.
I was like, okay.
Lower, higher melting point, correct?
Yeah.
All right, so that's based on hydrogen
Only 8%
bonding.
of women are colorblind and 1%
Oh,
of
go
men.
away. I'm going to have to, like, weed all this stuff out.
She's gonna have to edit this video too.
Very often, you will get a question like this, and there will be an arrow pointing here, 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 and here, and it'll say which is the hydrogen bond, and all of you are going to get it right. Right?
Yeah.
Wait,
Okay.
Can you put questions like that on our exam?
There'll definitely be a multiple choice question on your test, and if you had something like this, I might point like here, which of the following is the hydrogen bond? I might point here, 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 and here. So is it A, B, C, or D? Go away. It's C.
It's not.
All right. So those are the very easy types of questions that you could be asked. The other point I really want to make, it says when a substance undergoes a phase change, this is due to the breaking of the, this is really important, to the breaking of IMFs, not the breaking of covalent bonds. Be very careful. When a substance melts or boils, the IMFs are broken, not covalent bonds. And we'll pick up next time with the liquid state. We talked about water a little bit. I want to show you that video
Wait, when did
so you can see some of the properties of water, and we'll pick up with that next time.
wait, what year
And
did
let
the
me
liquid
cover that
state?
as well. So this is just the very beginning of the intermolecular forces. We'll get into it a lot more next time.
It's 11:03.